Now, you may have come across sometime between now and then some term known as an orthogonal vector, right? Or perhaps even just orthogonality of some vector. And this is actually precisely what we'll be considering today, and later on we can actually tie this into spin when considering quantum computing in terms of just a mathematical and computational representation of these c-bits or in terms of qubits. And so, primarily, if you look from a geometric sense, to sum it all up before we even begin, orthogonal vectors are quote-unquote perpendicular to one another. And let's begin defining what perpendicular means actually by considering and going back to vector addition. So if you have some sort of graph here, right, and let's say you have some vector, some ket vector A, which is 31, and we have some other ket vector B here. B here defined as, let's say 1, 2, right? Then we want to find the sum of A plus B. And if you may also recall, this is equivalent to B plus A. And we can show that visually in a moment, right? We want to figure out what that is. Now, from a mathematical perspective, that is, you can just add them essentially straight across. So it's 3 plus 1, which is 4, and 1 plus 2, which is 3, as we have covered previously. However, from a visual perspective, what this basically shows is if we show little hash marks for each individual unit on this graph, where each one is 1, 1, there we go. And then from a visual perspective, what it will look like is 3 over 1, 2, 3, right, and 1 up. So this is your A vector plus B, which is 1 over, right? 1 over and 2 up. 1, 2, right? And so their sum is drawn from the tail end to the head of your given vector, and this is what it looks like visually. Of course, you can also go in the other direction, right? Where you start with B, so 1 over and 2 up plus A, which is 3 over and 1 up, and which once again results in the same vector of the same magnitude. Now, looking at this representation, this graphical representation that we have here, there may be a couple of shapes that you may deem a little bit familiar. More specifically, we are taking and going to be looking a little bit closer at this shape that we have right here. And if that isn't entirely clear, we're going to be considering triangles. Now, you may recall from your good old geometry days the Pythagorean theorem. Let me make sure I know how to spell first. Alright, and so in that sense, it defines a given relationship between the sides of a triangle. We name them A, B, and C here, where A and B are very different from your ket vectors up here, just as a side note, right? And where it basically says A squared plus B squared equals C squared. Now, looking perhaps at just this diagram that we have here, nothing may entirely seem to pop out to you. However, if we elect to redraw it in a slightly different way, let's reconsider the situation. Let's say this is your A vector. Let's say this is your B vector. And let's say this is your the sum of these two vectors, right? Let's say they form a right triangle. Then clearly we all of a sudden have almost analogous or relationship right here between your triangle and the sum of these vectors that we have. And so based on what we've just shown you through the Pythagorean theorem, we can clearly state that the magnitude, and recall in this case the magnitude can be represented by the length, so the magnitude of your ket vector A squared, right, plus the magnitude of your B vector, your ket named B squared, should be ideally equal to the magnitude of A plus B, the vector it forms, squared. And so that's a kind of generic relationship that we can define based on these two vectors that are essentially at right angles to one another. And if we think of that a little bit more, this once again is what is defined as a orthogonal set of vectors. Now let's move on from there. Let's consider what orthogonality implies in a sense, and in a deeper sense. Now, one of the first results and one of the first claims that I'll make is that your vectors, your ket vectors A and B, are orthogonal if and only if, right? And this can be rewritten as IFF if needed, if and only if their vector sum A by B, or vice versa, is equal to 0. Now, how in the world can I even make that claim? Right, let me shrink this little claim that we have here and put it to the top. How in the world can I make such a claim? Now, if we consider it, let's start by taking the properties that we defined earlier. That is, the magnitude of A squared plus the magnitude of B squared is equal to the magnitude of A plus B squared. And this only works if they're at right angles to one another. Now, let's ignore this side for now. This is, quite easily broken down. We can see, it's quite straightforward. And let's take a look at this specific portion that we have here. Now, let's begin by finding again the addition, the sum of A plus B. And let's say A is defined as your ket vector A, right, is defined as A1 and A2. These are just their two terms. And let's say B is defined as B1 plus B2. B1 and B2. Now, in that sense, and this is just using two terms, not to be too complicated here, if we add them together, fundamentally, what we have and what we end up is something similar to this, right? So A1 plus B1, and then A2 plus B2. So far it's quite straightforward. Now let's begin by considering what this being squared and its magnitude being squared is. And if we were to consider precisely what its magnitude was, keep in mind that is approximately the same as essentially rewriting it in the following way, right? As we defined earlier, it is similar, just taking its vector product by itself. The Braun-Ketz version of it. And so if we were to continue writing this out in the long, taking it the long way, it would look something along the lines of this. And to save you some time, let me really quickly make sure I've got everything down. Again, just writing out their products. And then going on from there and multiplying it out. You may recall some of this from our multiplying vectors and matrices video. Let me really quickly just clear the space and make sure you have enough room to write out all your work. Okay, and just continuing on just from an algebraic perspective and fully expanding out what we have here. And then going on to group together our like terms. And by like, I'm merely referring to, for instance, A and A, and then B's and B's, and so on and so forth. More specifically, and let me make sure I get this out and completely written out for you, this is equal to A1 squared plus A2, right, squared plus B1 squared plus B2 squared. And let me put parentheses around these just to make them a little more clear, plus 2A1 B1 plus 2A2 B2. Right, and if this here doesn't seem quite familiar quite yet, you may start feeling a little bit like this is starting to resemble something at the very least. And more specifically, actually, if we go back to what lengths of and the magnitude of A and B are, this is actually equal to the magnitude of A. Because if you recall, let me just do a little bit of a side note over here, right? For instance, the magnitude of A is equal to the vector lengths, the vectors A multiplied by itself, the Braun-Ketz version of it at least, which is basically equal to, for instance, A1, A2 multiplied by A1, A2, right? which is equal to a1 squared plus a2 squared. And that same, essentially that same property can be repeated for b as well. So this is fundamentally, let me make sure I've got the right color here, this here is fundamentally equal to the magnitude of ket A plus the magnitude of ket B squared. I'm sorry, there's a square on the A as well, right? Plus, and if we look a little bit closer, right? If we look a little bit closer, this is fundamentally equivalent to taking 2, right? Factoring out the 2 times your lengths A and B. Alright, so we've gone all the way from, taking this up here to down here. We've just basically expanded it out in a sense in terms of vectors. So what does that mean for our original statement? Let me clear the board once again, and let's review what that original statement was, and let's make sure that we have taken enough steps to actually support what we just said. Alright, so just to briefly recap, we want to make sure that two given vectors A and B are orthogonal if and only if they're essentially the product of their brackets is equal to 0. Now, we have just shown here, and let me erase this part here in case that confuses anyone. What we've just shown here, as we previously stated, is essentially that this can be written on the following way: the magnitude of A squared plus the magnitude of B squared plus 2 times the product of A and B. And this here is just a generic representation for any vectors A and B. This statement that we have up here, however, more specifically applies only if A and B are at right angles to one another, as we established earlier according to the Pythagorean theorem. However, these two can only be true if this statement here clearly is equal to 0, because these two right here, these two terms match up, and similarly these two terms match up, and these two terms right here match up. So in order for these both to be true, 2 times A, right, and B must be equal to 0, and if you factor out the 2, again A times B must be equal to 0, and that's where the concept of whether or not A and B as the vectors are orthogonal and whether or not how you can prove that in a sense is true. And so let's take one quick example. Let's define 3 ket vectors, and let's say A is 3, 1, just going back to our earlier instance, and let's say B, or ket vector B is equal to, let's use easy numbers again, 1 and 2, and let's say our ket vector C is equal to, let's say, negative 2 and 6. Right. Now, what we want to be able to show is that for some two vectors, their product, right, is going to be equal to 0. And so let's start with A, right? Let's multiply A by B, which is basically like saying 3 and 1, right, and 1 and 2. And if you remember from our vector multiplication, you match these first two terms, which is equal to 3 plus 1. I'm sorry, 3 times 1, which is 3, plus, right, and you match your second two terms, 1 and 2. 1 times 2 is equal to 2, which is equal to 5. And then let's consider the next combination that we have here, which is B times C, right? And writing that out once again, 1 and 2 multiplied by negative 2 and positive 6. If you match them up, 1 times negative 2 is negative 2, and this is basically just going through the algebraic kind of notions, plus 12, right? 2 times 6 is 12, which is equal to positive 10. And lastly, you have A and C, right, which is 3 and 1 multiplied by negative 2 and 6. And maybe if you're plugging this in from a sort of common core kind of mathematics perspective, you may notice that if you take these as points and you try to calculate their slopes relative, for instance, to the origin, you might notice that these are perpendicular to one another. And interestingly enough, A and C, when paired together, do indeed equal 0 when you multiply them. And because A and B and C do not equal 0 when you multiply them, right? Then, in that case, A and B are not orthogonal relative to one another. B and C are not orthogonal vectors relative to one another, but A and C are indeed. And so from a more general perspective, actually, if you take a given set, a given group in a sense of vectors, right, then we start coming up with these different relationships between one another. And if you have a set of a given number of, n vectors, some set of some n vectors that are all mutually orthogonal to one another, then you have what is known as a orthonormal basis. Right? Now, if we break down, orthonormal basis. All right, and if we break down what orthonormal basis and what orthonormal means, if you just look a little bit further, you notice ortho, right? It is basically just referring to orthogonal, right? And normal here is normalized, right? And in terms of normalized, this is merely referring to like a unit of something. Now, this these orthonormal bases, these sets essentially can be especially useful. Now, your standard basis, right? Let me make sure I wrote this down. Your standard basis is typically expressed as something along the lines of 1, 0 and 0, 1. Right? So these two ket vectors, B1, and we'll call them B1 and B2. Right? And so these standard bases, maybe if you've seen like your classic computers, if you've seen binary numbers, they seem pretty straightforward. And so essentially your two two-dimensional vectors can be written and grouped together in the following way. Right, and if you check and go through all those properties that we just went over in regards to orthogonal vectors and these two vectors that are put together, and make sure that they fit everything within this set, all the possible pairs, which there just happens to be one pair, does indeed fit that definition. And so later we're going to figure out other ways and other examples of bases that are considered indeed orthonormal, and what that means in terms of spin. Alright, but that's all for today. So if you have any questions, please do not hesitate to visit the qmunitytech website. And again, stay curious and keep on learning.